Hello, welcome in the 10th lecture of my course Convective Heat Transfer. In this lecture, we will be doing some numerical sums based on flow over flat plate, whatever we have learned in the last 9 lectures. Okay. So, first let me give you the problem statement. As first problem, we will be doing this: estimate the heat loss from a vertical wall exposed to nitrogen at 1 atmospheric pressure. So, 1 atm pressure and 4 degree centigrade. Okay. The wall is 2 meter high and 2.5 meter wide and is maintained at 56 degree centigrade. The average Nusselt number over the height of the plate for natural convection is given by, so this is a natural convection case, so given by this formulation. So, you have to use this. The properties of nitrogen at mean film temperature. So, you can see the film temperature, mean film temperature will be 56 plus 4 divided by 2, and that is actually 30 degree. So, the properties are given, rho, k, nu and Prandtl number, these are given. Okay. So, you have to find out what is the heat loss from the vertical plate. Okay. So, this problem is related to natural convection over a flat plate. So, let us try to do this problem first. Okay. So, let me tell you how to solve this problem. So, first as we are trying to do natural convection problem. So, important thing what we need to evaluate is the value of beta, because beta is there in Grashof number. Okay. So, beta, it is nothing but volumetric coefficient of expansion. So, that for natural gas, ideal gas like nitrogen, we can write down is equals to 1 by temperature, 1 by T. Okay. So, here the temperature we can take as 30 degree centigrade. So, average temperature is 30 degree centigrade, which means 303 Kelvin. So, this is 1 by 303. So, which is actually equivalent to 3.3 into 10 to the power minus 3, 10 to the power minus 3, and unit will be Kelvin to the power minus 1. Okay. So, first evaluation of beta for nitrogen. Okay. So, for nitrogen we can do in this fashion. Okay. Next, as we have found out beta, let us try to get the value of Grashof number. So, Grashof number will be nothing but G beta. Okay. Then you are having surface temperature minus free stream temperature. Okay. Then we are having H cube, height of the plate, a height cube divided by nu square. Okay. So, nu for the nitrogen at mean temperature is given in the problem. Okay. So, let me put the values. So, this becomes 9.81 into 3.3 into 10 to the power minus 3, the value of beta, and then we are having Ts as 56 and T infinity as 4 into H is nothing but 2 meter high. So, 2 meter high. So, we are having actually 2 meter cube. So, 2 cube divided by nu square. Nu is also given in the problem. You can see nu is given over here as 15.63 into 10 to the power minus 6. So, that we will be putting over here 15.63 into 10 to the power minus 6, okay, whole square. Okay. So, if we find out Grashof number like this, Grashof number comes out to be 5.51 into 10 to the power 10. Okay. So, this is the value of my Grashof number. Okay. So, this is the value of my Grashof number. Now, already for this type of case in the problem, the Nusselt number correlation is given as Nusselt number is equals to 0.13 Grashof into Prandtl to the power 1/3, where Prandtl number is known as 0.6713 at mean temperature 30 degree centigrade. So, this we can use and we can find out the Nusselt number. So, Nusselt number is actually H by K. So, mean heat transfer coefficient into height, okay, of the plate into divided by K. This is nothing but equals to, as per the correlation, 0.13, then Grashof into Prandtl, okay, Grashof into Prandtl to the power 1/3. Okay. So, if you use these values of Grashof and Prandtl, it comes out to be 0.13 into Grashof number we have got 5.51 into 10 to the power 10 into Prandtl number is given in the problem 0.713 to the power 1/3. Okay. So, ultimately you get the Nusselt number as 441.934. Okay, 441.934. Now, if you try to evaluate the value of heat transfer coefficient, so H bar will be Nusselt number 441.934 into your K. So, K is also given in the sum as at mean temperature 0.026. So, 0.026 okay, divided by H, which is 2 meter. So, if you do so, H comes out to be 5.745 watt per meter square Kelvin. Okay. So, this is the heat transfer, average heat transfer coefficient we have found out. Okay. Now, if we try to find out what is the heat loss. Okay. So, heat loss, let us say Q is the heat loss. My answer, what I need to find out. So, heat loss will be actually H average. So, average heat transfer coefficient into area into surface temperature minus free steam temperature. Okay. So, let me put the value of H first. So, this is nothing but 5.745 into area is nothing but your height and width. So, height is 2. So, it is 2 into width is 2.5. Okay. So, 2.5 meter 5 meter wide plate. So, this into Ts minus T infinity is 56 minus 4. Okay. So, if you calculate this one, so overall heat loss becomes 1494 watt. Okay. So, this is my heat loss Q. Okay. So, heat loss Q, the final answer comes out to be 1494 watt. Okay. So, let me show you the final answer over here. So, final answer is actually this one 1494 watt. So, in this way you can actually do sums for natural convection. Let me show you the next problem. So, next problem goes like this, water flow with a velocity of 0.25 meter per second over a 75 centimeter long plate, okay. Water flows with a velocity of this over a 75 centimeter long plate. Free steam temperature is 35 degrees centigrade. So, T infinity is 35 degree and surface temperature. So, surface is having a constant temperature 85 degrees centigrade. So, you need to find out or you need to derive an equation for the thermal boundary layer thickness in terms of the Reynolds number. So, delta T in terms of RE you have to find out, and then you have to determine the heat transfer coefficient at x equals to 7.5 centimeter and 75 centimeter. So, H you at 7.5 and 75 centimeter you have to find out, and finally, you have to get the heat transfer coefficient, heat transfer rate for a plate having 50 centimeter width. Okay. So, this problem is once again flow over a flat plate, and this time it is actually forced convection case. So, let me see how this problem can be solved. So, let me first erase the previous one and give you the idea how this problem can be solved. And in this problem we are having water. So, your water properties will be very important. You can get the properties from your steam table. So, we will be also using data from steam table to get the water properties. Okay. So, first let me find out what is the mean temperature. So, let us say the mean temperature TF is actually, mean temperature for the fluid is actually, you can see 35 plus 85. So, 85 plus 35 divided by 2. So, you get this is actually 60 degrees centigrade, okay, 60 degrees centigrade. So, at 60 degrees centigrade if you try to find out the properties, so K will become for water from steam table you can get 0.6507 watt per meter Kelvin, okay. Then Prandtl number if you see from steam table once again it will come as 3, okay. Nu it will come as kinematic viscosity, it will come as 0.4748, okay, into 10 to the power minus 6, okay, meter square per second, okay. And next let us try to find out first what is the Reynolds number. Okay, so as we are having two cases, so 7.5 and 75. So let me first try to find out what is at 7.5. So at x equals to 7.5 centimeter, okay, 7.5 centimeter. So Re is actually u infinity x, okay, by nu, and u infinity is nothing but 0.25, okay, x is 0.075, okay, and divided by nu, that is 0.4748. From the property table just now we have got 10 to the power minus 6. So ultimately this Re comes out to be 3.949 into 10 to the power 4. Okay, so you see it is actually less than 5 into 10 to the power 5. So we can say this is actually a laminar zone. Okay, so this is actually a laminar zone. Okay, now if it is laminar, quickly we can find out the Peclet number. Okay, so Peclet number is nothing but Re, by the way, this is Rex at 7.5 centimeter. So Rex into PR, so this becomes 3.949 into 10 to the power 4 into Prandtl number, which is 3. Okay, so if you do that, so Peclet number, okay, so Peclet number becomes 11.85 into 10 to the power 4. Okay, so this we have got Peclet number. Now first part let us try to answer. So we have to derive an equation for the thermal delta T, we have to derive as a part of as a function of Reynolds number. So part A, let me do it over here. So part A, if you try to do, so for Prandtl number is equals to 3, okay, and if we define the non-dimensional temperature T as T minus Tw by T infinity minus Tw, similar type of non-dimensionalization we have done so many times earlier for flat plate case. Okay, so this will be equals to 1 at okay, at eta equals to 3.2. Okay, so this you can find out whenever you solve the energy equation, whatever final form we have given, and you can find out that at eta equals to 3.2, theta becomes 1. Okay, so if we take this one, so we get 3.2, which is the value of eta, is nothing but delta T root over of, now the non-dimensionalization of eta, non-dimensionalization of delta T is nothing but u infinity nu into x. Okay, so here 3.2 is equals to delta T by x. Okay, if you take x out, so it becomes u infinity x by nu, okay, which is nothing but actually Reynolds number. So you get delta T by x is actually 3.2 by root over of Rex. So this is the relationship we have actually desired in the part A, that what is the relationship between delta T and Rex. Remember here I have taken the help of thermal boundary layer equation, theta will become 1 whenever eta becomes 3.2. This came from the solution of the boundary layer equations. Okay. Let me go to the part B. So part B over here. So we need to find out the heat transfer coefficients. So let me write down the heat transfer coefficient. So Hx, okay, heat transfer coefficient can be written as K into and then u infinity nu into x, okay, into theta dashed 0. Okay, so theta already we have defined over here. So theta dashed 0, this also we have derived in our lecture. So we will be taking the help of this H. Okay, so let me try to find out what is theta dashed first. So we know theta dashed is actually 0.332 into Prandtl number to the power 1/3, okay, as our Prandtl number is equals to 3, which is in the range of 1. We have seen 3 different cases, Prandtl number is equals to 1, and then we have seen Prandtl number less than 0 and Prandtl number less than 1 and Prandtl number more than 1. So we are taking the Prandtl number equals to 1 zone, but as it is exactly not equals to 1, it is 3. So we are taking Prandtl number to the power 1/3, which actually we have seen in case of higher Prandtl number zone. So constant we are keeping same, but Prandtl number to the power 1/3 we are keeping for from Prandtl number greater than 1 cases. Okay. So this is theta dash we have got. So in our case theta dash will become 0.332 into 3 to the power, Prandtl number is 3, so 1/3. So this becomes theta dash becomes 0.479. Okay. So we have obtained theta dash. So next task is to put the value of x and theta dash over here to get the value of hx at different level. Okay. So if we do so, so let us do it over there. Okay. So if we do so, so for the second part we will be using the formulation whatever we have just now derived. Okay. So let me come over here from here to here. So if we see that h, okay, heat transfer coefficient at, okay, x equals to first let me do it for 7.5 centimeter. So 0.075 meter. Okay, 0.075 meter, that becomes obviously this formula we will be using. The value of k is actually we have found out as 0.6507. So let me take that value. So 0.6507 multiplied by 0.479 is the value of theta dash. So this will be writing over here. So 0.479 and then multiplied by root over of, okay, root over of, here we are having u infinity, the value of u infinity is 0.25 meter per second given in the sum, 0.25 meter per second given in the sum, okay, and then divided by nu into x. So nu is nothing but 0.4748 into 10 to the power minus 6. Okay, minus 6, and then we are having x is nothing but 0.075. Okay. So if you calculate this one, so h at x equals to 0.075 turns out to be 825.5 watt per meter square Kelvin. Okay. Just the same thing can be found out for x equals to 75 centimeter, which is nothing but 0.75 meter. The value of last one, it will be changing, and you can do the same sort of calculation. You can find out this turns out to be 261 watt per meter square Kelvin. Okay. So first two part already we have answered. So let me show you the last part. In the last part it is asked, determine the heat transfer rate for a plate of 50 meter wide. So here we need to find out the heat transfer rate as a part of C. Okay. So let me show you how that can be done. So C is over here. So for C, as we have already found out what is H, let me do what is H bar, or average heat transfer coefficient. Average heat transfer coefficient will be 2K by L into root over of REL into theta dashed 0. So this also we have shown in the lecture. So from here we will be finding out the value of H bar. So H bar is nothing but, let us put the values, 0.6507 is the K, L is nothing but 0.75 meter, REL we have found out, over here, REL is actually 3.949 into 10 to the power 5. So that we will be putting over here 3.949 into 10 to the power 5. Okay. And then we are having theta dash 0, which is nothing but 0.479. So if you calculate this one, so H bar becomes 522.1 watt per meter square Kelvin. Okay. So we have got H bar, this we will be using for finding out the finding out the heat transfer rate. So, Qt is the heat transfer rate, this becomes Tw minus T infinity into H bar into A. Okay. So, A. So, let me put the values. So, Tw is nothing but 85 minus T infinity is 35 free steam temperature, H bar we have just now find out 522.1 and area is nothing but 0.75 into the width is actually 50 centimeter. So, 0.5. So, ultimately this Qt becomes something around 9789 watt. Okay. So, this is the last answer, part C. Okay. So, let me show you all three answers over here as question 2. So, this is the first answer we have got, delta T is equal to 3.2 divided by root over of Rex into x. Second answer we have got for both the levels at 0.075 and 0.75, and last C we have got 9789 as we have shown over here. Okay. Let me show you another problem. The problem is like this. Air at 30 degrees centigrade flows with uniform velocity 4 meter per second over a flat plate. Okay. A tiny insect, there is a insect, this tiny insect find itself at location O over here, location O near the surface of the plate. Okay. Air velocity u at this location is too high for the insect. So, the velocity whatever it is facing, that is too high for the insect. It wants to take 1 millimeter step to any of the locations. So, it wants to move 1 millimeter. So, it is having 4 options to go in this direction, to move in up, to move down and to move in the left hand side 1, 2, 3, 4 respectively. What will be the velocity u at these locations if the insect starts, that means O point is 150 millimeter, 2 millimeter, x and y respectively. Is the then I have asked, is the insect inside the viscous boundary layer? Though we have shown the figure like this, but is the insect inside viscous boundary layer? Okay. So, this is a typical problem of flow over a flat plate. Okay, and we will try to see this one here. Nowhere heat transfer is involved. We will be doing this sum for only for the fluid mechanics velocity boundary layer. Okay. Only the properties we need to take at 30 degrees centigrade for the air. Okay. So, let me show you this one, very simple fluid mechanics related problem. So, let me show you the solution of this problem. Many of you can readily do it because already you have knowledge of fluid mechanics. So, we will be using the same over here and try to find out the solution of the present problem. Okay. So, as I said, we are having actually flow over a flat plate. So, let us say this is the case, we are having a flat plate like this and there is some sort of inflow. Okay. So, let us say the inflow velocity is V infinity. Okay, and this is my x direction. Okay, and this is my y direction. So, here we will be having a velocity boundary layer. Let us say the boundary layer thickness is actually delta. Okay, and we are having the insect at the beginning over here at O position. Okay, and it is having 4 different options to move in 1, 2, 3 and 4 respectively. 1, 2, 3 and 4 respectively. Okay. So, the question is actually at different locations what velocities it will be getting. So, to solve this problem, first we need to understand whether it is in laminar zone or turbulent zone. So, let me first check whether it is laminar or turbulent. So, first we will be finding out the Reynolds number. Okay. So, Reynolds number is nothing but 4 into, first let me see what it is getting at one position. If it is at one position, then definitely your x will be 150 plus, and as it is taking 1 millimeter leap, so it is 151 millimeter actually. So, let me put 151 for the x for the one position first. So, 0.151 0.151 because that is the extreme limit. So, that will be having the highest Reynolds number. So, that we try to find out divided by 16.01 into 10 to the power minus 6. If one point is laminar, then obviously this 2, 3, 4 will be laminar. Okay. So, if we try to see this by the way, this 16.01 10 to the power minus 6 is actually the kinematic viscosity of air at 30 degrees centigrade. Okay. So, if you see that one, it will come out as 37726, okay, which is definitely less than 5 into 5 into 10 to the power 5, okay, which is the limit for this one. So, from here we have understood as it is laminar, okay, so we can actually use our Blasius law, okay. We can actually use our Blasius law, whatever we have learnt in fluid mechanics. So, let me start using Blasius. Okay. So, first we know for Blasius the similarity parameter is eta, which is nothing but y into root over of u infinity by nu into x. Okay. So, this is my eta similarity variable. From Blasius also we know that delta by x is actually 5.2 divided by Rex. Okay. So, this also we have seen in our fluid mechanics knowledge from Blasius equation. So, this is from Blasius. Okay. This is from Blasius. So, if we try to use this, let me first find out the value of eta for 0th location. Now, one by one we have to do for all 5 locations. First, let us see what happens at 0th location. So, if you see at 0th location, so it becomes y is nothing but it is actually 2 millimeters. So, 0.002 root over of u infinity is given as 4. So, 4 divided by nu already just now we have used 16.01. This you need to find out from air property table 10 to the power minus 6, and then we are having x at 0 location is nothing but 150 millimeter. So, that means 0.15. Okay. So, if we use this eta comes out to be at 0th location. So, eta at 0 we can write down, this comes out to be 2.581. Okay. Next task is to find out what is the value of u by u infinity, and subsequently we can get the value of u because velocity is required. So, to get the value of u by u infinity, we need to see the solution of your Blasius equation, which is nothing but f triple dash plus f double dash is equals to 0, okay, with its corresponding boundary condition. So, let me not go over that solution over here, but let me try to give you a table for different eta values and subsequently different f dashed values, okay, because f dashed is nothing but u by u infinity as per Blasius we know. Okay. So, let me give you those values. So, at 0 boundary condition we know that eta 0 means f dashed 0, okay, from your no slip boundary condition it is coming. Then let me give certain interval. So, 0.4 is 0.13277, okay, then 0.8 is actually 0.26471, and then 1.2 is actually 0.39378, then 1.6 is actually 0.51676, then 2 is actually 0.62977, and then 2.4 is actually 0.72899. Then if we proceed further, 2.8 is actually 0.81152, 3.2 is actually 0.8766, and then 3.6 is actually 0.92333, and finally let us write down up to 4 only. At 4 0.95552. Okay. So, this list can be lengthened further, but for our present case up to this will be sufficient. So, you see our eta value at 0 is 2.581, which lies in between these two. So, if we do little bit of interpolation, then we will be finding out this at this eta f dashed, which is nothing but u by u infinity, is equals to, if you do the interpolation between these two, you will be getting this is nothing but 0.766. And now, as u infinity or v infinity, those are same actually. So, that is known to us, which is nothing but your 4 meter per second. Then from here we can get u at 0 at x 0. Okay, let me not write down x 0. Okay, so let me write down at 0. Okay, because x is having some other value at 0. So, u at 0 is actually 0.766 into 4, 0.766 into 4, which is nothing but 3.064 meter per second. Okay. Now, if you proceed in same way for eta 1, eta 2, eta 3 and eta 4, which will be only changing the value of x. So, x and y. Okay. For example, for one position y remains 0.002, but x will be 0.051. Okay. For two position y will be 0.003 and x will be 0.15. For three position y will be 0.002 and x will be 0.149, and subsequently at 4 position y will be 0.001 and x will be 0.15. So, if you do like that, you will be finding different values of eta, and using this table via interpolation you have to get the value of f dash, which is nothing but u by u infinity, and subsequently multiplying f dash by u infinity, which is equals to 4 meter per second, you can get the velocity. So, let me show you the final table what we obtain. So, let me give you, this is the location in the first column, then we are having the corresponding x values, corresponding y values, okay. Then we are having eta values, okay. Then you are having corresponding u by u infinity values, and finally if you multiply by 4 it is becoming u for different locations. So, if you try to construct a table like this, for location 0 already we have done, x was 0.15, y was 0.002, then eta we have found out as 2.581, okay. U by u infinity we have got as 0.766, and finally u came as 3.064 meter per second. Let us give you the final answers for all 1, 2, 3, 4. For 1 it will be 0.151, for 2 for 1 it is 0.151 x, y is 0.002, for eta you will be getting, this is nothing but 2.573, u by u infinity or f dash comes out to be 0.765, and finally u comes out to be 3.06. Similarly, if you do the rest at 2 position, x will remain 0.15, y will be becoming 0.003, and then eta will become 3.872, and then f dash will become 0.945, and subsequently u become 3.78 meter per second. For location 3 it will be 0.149, and then y is 0.002, and then eta becomes 2.59, and then u by u infinity or f dash becomes 0.768, and finally u becomes 3.072. And for the last location, fourth location, you can get the x is 0.15, y is 0.001, okay, and then eta is 1.291, subsequently f dash is 0.422, and finally the velocity comes out to be 1.688. Now, as the insect is not loving the velocity, so from here at different locations from the velocity you can find out definitely fourth location is preferable for the insect. So, it is better suggested that it can move down 1 millimeter leap, and it will be facing least amount of velocity. Okay. So, this answer we have found out. The last part of this answer is actually whether the insect is inside the boundary layer or not. To find out that portion, let me first calculate what is the boundary layer thickness. Okay. So, that I will be doing it over here. So, for finding out the boundary layer thickness, we know from fluid mechanics equation, here also we have shown delta is actually 5.2 divided by root over of Rex, okay, into x. Okay. So, this equation already we have seen. So, let me put the values. So, here you see the boundary layer as it will be growing up. So, maximum boundary layer thickness will be somewhere at 1. Okay. So, let me put the value of x at 1 to get the maximum boundary layer thickness. So, you can find out this is nothing but 5.2 divided by root over of Rex. Rex for 1 already we have shown you the value came out 37, okay, 726, right, and then your x value is 0.151. Okay. So, ultimately you get your boundary layer thickness at 0.1 is 0.004 meter. So, that means 4 millimeter. Now, you see the insect is nowhere moving, it is starting from 2 millimeter, at the most it can go if it takes one leap up. So, it can take up to 3 millimeter, which is obviously lesser than 4 millimeter. So, that the insect will be always remaining in the boundary layer zone. Okay. So, this is the answer for this question. Let me show you the answer over here. So, first obviously the velocities I have shown over here in the table, I have not shown the table over here, but the boundary layer thickness I have shown over here as delta equals to 0.004. Okay. So, with this I will be ending this lecture. In our next lecture we will be starting a new thing, internal flow thing. So, we will be actually discussing about forced convection in duct. Okay. So, if you have any query related to flow over flat plate or any other generalized questions about convection heat transfer, please keep posting on this discussion forum. Thank you very much.